Welcome to NPTEL course on power system protection. We are with module 8 on differential protection of transmission line and bus bar. In this lecture, we will discuss on the protection of bus bar, where we will see different arrangements for bus bar, and then the different perspective of bus bar protection, including frame leakage and the differential protection. Bus bars can be arranged in different ways. So, if you see different substation in power system, we will find different combinations of isolators, circuit breakers, line connections to bus bars, single bus, multiple bus, and there are other options. One way of categorizing the bus bars is that it can have single bus, single breaker, single bus, single breaker, double bus, or breaker and half bus, where you can say that we have two buses and then the connecting lines, and in between you can say that we have three breakers. So, most widely used you can say that in high voltage substations, the breaker and half, and the single breaker, single bus widely used in across distribution or low voltage system perspective. And so, the bus arrangements are not limited to these three, there are other options available also. But point to note here is that bus bar is very vital element in the substation or power network, where you can say that the energy concentration of the several you can say that incoming and outgoing lines happens to be there, and a fault in you can say that in bus bar leads to worse situation, and that requires you can say that very fast and precise fault clearing in order to avoid widespread implication on the power system stability issue and so. Two categories can be observed, we can say that on the protection aspects, we say fixed bus approach and the switchable bus approach on the protection perspective and so. So, in the fixed bus approach, single bus, single breaker, ring bus, breaker and half, double bus with double breaker, and in the switchable bus we have main bus and transfer bus, double bus and transfer bus, double bus and single breaker. These are the different classes we can talk about here. In the fixed bus approach, like here we have a bus and the corresponding the switches, isolators, all are connected you can say that to the particular bus, and so in the switchable bus you can say that we can have an auto switch you can say options available. So, the corresponding protection arrangement, all these things depends upon whether it is a fixed bus approach or it is a switchable bus approach into the system and so. And as already mentioned that bus bar protection is critical, and then you can say that the protection schemes depends upon the particular arrangement of the buses. One simple approach which is being used is for the frame leakage protection perspective. So, if you see this you can say that the connection diagram here, we have a CT connecting you can say that to the frame leakage frame to the earth, and on that path this CT you can say that connects to an you can say that overcurrent relay, and in case of you can say that failure of any insulator also you can say that this path you can say that has sufficient current to operate the corresponding overcurrent relay perspective. And this is very simple, and this can you can say that use an instantaneous overcurrent relay itself, and this you can say that the particular setting of this protection scheme is around 30% of the minimum fault current of the system, and because this is related to the earth fault and so. So, therefore, you can say that this relay is pretty sensitive you can say that to to the arc fault perspective of the bus bar fault. There is another simple approach on interlocking scheme, where you can say that overcurrent relays are there for, you can say that, to the outgoing, you can say that, feeders and to the also the incoming feeders. Now, what is being done that in case of fault, external fault or a fault in the any of the line, the corresponding, you can say that, relay which takes the decision through the that signal, you can say that this, you can say that the incoming bus, you can say that relay is being blocked. Whenever this, you can say that any of, you can say that these relays, you can say that does not find a fault, then this will not be blocked, ensuring that there is an internal fault to the bus bar. So, this you can say that about the simple interlocking scheme based on the overcurrent principle. Only one point here is that a short coordination timer is required between, you can say that, these outgoing, you can say that, overcurrent relay and this incoming bus, incoming, you can say that, overcurrent relay. Widely used in for the bus bar protection is the differential protection. So, in differential protection, for that perspective we have already learned on transformer protection, and earlier lectures we have learned how transmission line protections can be there. In bus bar protections, we do not have, you can say that, issues like inrush current, overfluxing or phase compensation, and so it is pretty simple and based on, you can say that, simple KCL applications applications to the system. So, like earlier, you can say that the cities are connected such that the I operating, you can say that, becomes 0 for normal operating condition, summation of this magnitude of that current for the differential protection perspective. But for internal fault, you can say that all the currents enter and the city connections are such that the I operating becomes significantly high, and that is nothing but the fault path current. So, that we already know for that internal fault condition. For external fault condition, similar to the normal operating condition, the corresponding summation of all the currents should be 0, but this may not happen, you can say that, in case of city saturation and or so. Two approaches for the differential protection for bus bar. One is called the low impedance, the other is called the high impedance. First, the low impedance differential protection approach for the bus bar protection 87B. So, as already mentioned, the I operating is a summation of this, I restraining is summation of this, and the tripping, you can say that, characteristic just like simple differential relay, I operating is greater than IPU and I operating is greater than M I restraining, the way you can say that we talk about here. So, this slope remains typically between 0.25 to 0.8 and maybe higher also, and the IPQ, you can say that pickup current is typically set 130% of the maximum feeder current, or you can say that M is the percentage biased vector. So, 130% of the maximum feeder current, there may be multiple feeders. So, we have to consider the in which feeder we have the maximum current. Again, in the same, you can say that low impedance protection perspective, we categorize into two. One is that instantaneous approach and the other is phasor approach. So, earlier we have learned for the line protection and the bus bar for the transformer protection also how phasors can be applied, and so because bus bar is very critical element in the system from stability perspective, the protection should be as fast as possible. So, relays, you can say that, also use instantaneous or the sample based approach for the protection using the differential principle. So, here sample values are used, but to consider that to ensure that the fault is internal, you can say that, to the systems. So, n continuous, you can say that, instances are being checked about the to check the consistency of the decision. When compared with the phasor based approach, instances will have high tripping speed, obvious. Special attention to be given for the city saturation detection. For external fault city saturation, still differential current will be significant. So, that has to be ensured that we know the consider the way how CT saturation can be detected for external fault, that has to be applied here also. Modern bus bar protection based on sample value approach being widely adapted and satisfying IEC 61850 process bus application and so. So, what is being done in the instantaneous or sample based approach? Two modes, 1 out of 1 very fast mode and 2 out of 2 slow mode. So, this is the considered broadly the corresponding scheme you can say that what is being applied in the schemes. So, we have a startup element which you can say that detects the rate of change of restraining current based on the rate of change of restraining current, and we have differential element the operating current. So, what is being done? If you see, you can say that here if both are level is high, say 1 then AND operations that will say high. So, checks for 1/4 of a cycle about the consistency, then if it satisfies that, then becomes count becomes 1. So, if this is 1, you can say that this you can say that becomes equal to 1 or high. Now, check this you can say that parallel path. Now, if this is high or 1, this is high or 1 at a given instance, negation of that. So, this becomes you can say that 0 or low. So, therefore, 0 or low output here. So, this you can say that becomes no delay, and this becomes you can say that again inverted. So, this becomes again 1. So, this is already you can say that 1 in this path and this is 1. So, therefore, you can say that AND operation gives 1. So, this is 1 out of 1 path OR operation and trips. So, once again for an internal fault, this becomes high, this becomes high, both are high. So, this becomes high and delay for consistency checking becomes 1/4 of a cycle. So, this count becomes 1. So, count becomes n equals to 1. So, this becomes high. Now, we come to this path because of the negations, this becomes 0 at that time for the internal fault. So, you can say that this is this becomes 0. So, this negation of becomes 1. So, 1 and 1 you can say that, or the high and high leads to you can say that 1 out of 1 approach. Now, see the other you can say that 2 out of 2 you can say that mode. In this case, what it happens you can say that if the output of the differential element is negative, that means that you can say that I operating is not significant. In this case, you can say that this will be 0 or low. So, therefore, inverted means this becomes high. So, this you can say that will be you can say that with the starter elements providing high, then this becomes high. So, this will lead to a delay of 150 millisecond. So, with this delay you can say 150 millisecond, you can say that if this becomes still you can say that high. So, therefore, you can say that this becomes 0, and then you can say that this 1 out of 1 you can say that will not provide any output. However, if you see this path now, if the corresponding you can say that these both are you can say that now the differential is high and this also high, for a consistently you can say that of n equals to 1 and then n equals to 2 means 1 not 1/4 cycle, half cycle. So, then becomes this equals to count becomes n equals to 2. So, this is 2 out of 2 path, and then because OR operation this becomes strip. So, this is when happens what in case of typically a situation of evolving external fault, then finally resulting into an internal fault, and this delay you can say that helps in doing that particular perspective, and the corresponding you can say that half cycle delay may you can say that give us this option of tripping for such a situation. The other one is high impedance fault, high impedance differential protection approach. The scheme happens to be like this, and the connection diagram is different than you can say that what we saw for the normal differential protections with low impedance approach. Here we have you can say that high resistance value which is connected to you can say that to an overcurrent relay, you can say that having high sensitive overcurrent relay. So, this is you can say the arrangement for the 87 Z for the high impedance path. So, this resistance value can be as high as you can say that a few kilo ohms also, and then you can say that it is connected you can say that in a mob approach this for the protection aspect, and if required you can say that a overcurrent relay can be also connected in this fashion. So, what happens here in this case is that in case of you can say that external fault, if any of the CT saturates, saturates for the external fault, that path you can say that becomes a low impedance path, and thereby I can say that the corresponding current flows through that path, because this you can say that all the you can say that you see here CTs are connected to the common point, and thereby the corresponding current to this you can say that high resistance you can say that path where the corresponding relay is being connected, the amount of current becomes insignificant. But for internal fault case, even though you can say that one CT or multiple all CTs may saturate, so the corresponding output you can say that here voltage becomes very high, and that you can say that in that case the corresponding you can say that through this path you can say that even though the resistance is high, the current becomes significant to drive the corresponding overcurrent here you can say that at 87 Z, and that results in you can say that the corresponding relay to operate you can say that for internal fault case. However, in this arrangement the corresponding CTs are specially you can say that they need to be you can say specially designed, or you can say that in that perspective. So, that the corresponding you can say that for this you can say that the requirement of satisfaction of this happens to be there. But note that in case of internal fault, the corresponding voltage may be very high, and that may be detrimental to you can say that for these gadgets like the high resistance, the resistor and other you can say that accessories here, and to protect that you can say that from that the metal oxide varistor you can say that is being added you can say that in parallel with these circuits. The 86 you can say the auxiliary lockout relay, which helps you can say that in the tripping mechanism. The advantage of this one is that the primary operating current can be set much below the circuit load, resulting in a high sensitivity. Disadvantages are the relay setting must take the CT secondary winding and wiring resistance into account, which must be kept low, and the CT knee point voltage must be known, and that is what I like to say that in the design process they need to consider special CTs and information, detailed information of the CTs also. All CTs should have the same ratio. This is another you can say that typical requirement, and should be also the same type of performance and so. Furthermore, the stability of the protection depends on the fault level. This simple for high impedance bus bar protection is widely used for the simple bus bar configuration, but not suitable for complex bus bar arrangements. So, we will see you can say that many applications in this oriented, but this has special requirement in the application perspective. We will see two examples. The first one is on internal fault and the second one is on external fault of the related to bus bar. So, this is you can say that a bus bar, and we have you can say that 3 lines connected to the bus bar, and an internal fault happens to be there in this bus bar, and the fault is of AG type in phase A only, agree. So, the associated CTs you can say that groups connected 1, 2, 3 that corresponds to the corresponding line 1, 2 and 3 feeder lines. So, in the pre-fault condition you can say that we have IA1, IA2 and I2A and I3A, these are the 3 line currents in phase A, and then you can say that if you apply KCL you can say that then the phasor you can say that shows that the sum will be 0. So, for this perspective as I already mentioned you can say that for the low impedance protection arrangement we have you can say that IP equals to 1.3 times of the maximum current. So, the maximum current happens to be there in the third line and this is 3.26. So, 3.26 of 130%, 1.3 gives you 4.2 ampere, and we have selected you can say that M the slope of the line of the percentage biased differential relay to be 0.5. This is about low impedance percentage by differential relay. For internal fault the current level not though significant, but it clearly shows you can say that there is an unbalance in the system here, and if you see the corresponding phasor you can say that positions. So, this becomes you can say that summation becomes non-zero, and that is why you can say that the KCL governs. Now, if you apply this you can say that the additions, the I operating in phase A, this is a phase A to ground fault, we are checking phase A only here. So, this summation becomes of these 3 phasors you can say that becomes 0 ampere for pre-fault. For you can say that during pre-fault condition the restraining current becomes you can say that significantly high 6.52. So, therefore, the relay will not go for operations during pre-fault condition. For a fault condition, to know you can say whether it is internal or external, the I operating A summation with those values what we have seen in the earlier slide. If you add, you consider all these things, they become 4.9 and the restraining current becomes 8 ampere. But the I operating you consider greater than IPU, that we have already checked, you consider earlier also that 130% of the maximum fault current. So, and the I operating A in phase A is greater than M I restraining 0.5 into 8 here is 4 ampere. So, therefore, you consider that even with the considered small value of you can say that internal fault situation and so also the relay is able to you can say that detect the fault correctly. In oscillograms you can say that if you see the situations, if you see here this phase A current is high, you can say that after this following the fault inceptions at this point. So, this you notice you can say that in all the L1, L2 and L3 all the 3 lines, and then you can say that if you go to you can say that the corresponding particular phase, the corresponding current magnitude you can say that increases you can say that during the fault situation. In all the you can say 3 phases the corresponding current you can say that happens to be this way, and then you can say that if you see the corresponding dynamic plot of this one, then you see the operating current to be you can say that the red one, and the restraining current you can say that M I restraining A you can say that becomes this one. So, because the operating current is greater than the M I restraining you can say that, so the relay will go for trip decision, and that is what you can say that the dynamic plot also said that the relay will consistently find the fault as internal fault. This case is for external fault. In bus bar you can say that the fault can be either insulator failure, or you can say that an external element faults on the you can say that buses and so, and there are numerous regions of faults and all these things. So, the consider you can say a fault of AB type in this case, an external fault you can say that this fault in maybe each in this case is in the line fault you can say that beyond the corresponding bus bar. Pre-fault condition, phase A current, phase B current in all the 3 lines, that what will the corresponding CTs will provide to the bus bar, and then this is the fault current you can say that which are the for phase A and phase B, because this fault is involved with phase A and B. So, that is why we are showing here these 2 phases. Similarly, you can notice for the phase C also, and these 2 you can say that phasor positions you can say that for this pre-fault and the corresponding fault you can say that are shown here. So, in pre-fault case the summation will be 0, and in case of you can say that here also this is by and large you can say that 0 you can say that in this case, because of the balanced nature of the for the external fault cases. For calculation of pre-fault, again the I operating in A phase A you can say that this becomes 0 and restraining current becomes significantly high 6.52. So, I operating you can say that current is does not satisfy you can say that IPU. So, that is why I can say it will not go for operation. Fault condition phase A, when you say you can say that in phase A the corresponding fault current is pretty small 0.03 as compared to the restraining current 8.68. So, the relay does not satisfy I operating greater than IPU, and that is why this will not go for operation. This is correct, because this is an external fault situation. For phase B also if you observe similar situation happens to be there, the corresponding pre-fault condition is 0 ampere for phase B and restraining current is 6.52 ampere. So, during the corresponding pre-fault condition it does not operate. For fault condition you can say that in phase B you can say that this also the corresponding value of operating current is pretty less insignificant as compared to the consider the restraining current of 7.67 amperes. So, in the phase B differential also it is being observed that it does not satisfy the requirement of I operating greater than I IPU, it implies this is an external fault. Now, there are also you can say that other you can say that arrangements, other you can say that protection schemes available in this one. In directional comparison bus relaying, a direction comparison bus protection system compares the direction of current flow in each circuit connected with the bus. If the currents in all circuit flows into the bus, a bus fault exists. Right? This is based on the directional informations. Directional link principle we have learned you can say that in earlier also in details using different principle including negative sequence and so. If the current in one or more circuit is flowing away from the bus and external fault exists, fault detectors are used in consider initiate the system, and this can be used either or both phase and ground faults and protections. And also this you can say that such you can say that different you can say that protection schemes for the bus bar also can be integrated, and they can be combined to make a more reliable decision also. The overall remarks on this you can say that perspective is that when compared to transformer differential protection, bus bar protection is more straightforward, but you can say that complex bus arrangements require separate protection for each bus zone that we observed from the very beginning. Bus bar differential protections can be categorized into two: the low impedance differential protection and the high impedance differential protection. High impedance differential protection is widely used, but it requires you can say that special cities for its applications. We also saw you can say that frame leakage protections, which is sensitive to you can say that to earth fall perspective, and so. So, bus bar protection is critical to the power system operation. It should be clear as fast as possible, so that system stability is not being hampered. Thank you.